Hi, I'm Colette Belinsky, and today I'll be presenting my project on using bioluminescence to study macrophage polarization. Macrophages are part of the innate immune system. They're highly phagocytic, and they play an important role in tissue homeostasis and regulating the inflammation response. So they polarize along a spectrum with M1 on one end and M2 on the other. So M1 macrophages are pro-inflammatory and anti-tumoral, and M2 macrophages are anti-inflammatory and pro-wound healing. And because of this, they're also pro-tumoral. So macrophages form a significant population within tumors, and they're called tumor-associated macrophages. They're generally considered to be M2 polarized as a result of influence from tumor cells, as well as the composition of the tumor microenvironment. These tumor-associated macrophages, or TAMs, assist with angiogenesis, tumor growth metastasis, as well as immunosuppression, and can increase a tumor's invasiveness. Utilizing bioluminescence to monitor gene expression is already pretty commonly used in circadian rhythm studies for mammalian and plant cells. Bioluminescent microscopy gives both temporal and spatial information. So we want to utilize bioluminescent microscopy to monitor macrophage polarization within the tumor microenvironment. So I utilized two methods for measuring luminescent intensity for this project: spectrophotometry for temporal information only, or microscopy, which gives both spatial and temporal information. So we created a few macrophage reporter lines that luminesce as a transcription factor tied to a specific polarization is activated. We've developed 3 lines so far. The constitutively active CMV labeled line serves as a bioluminescent control. And then we have 2 inducible lines, NF-kappa B is our M1 or pro-inflammatory marker, and STAT5 is our M2 or TAM marker. So to test the TAM reporter line, I seeded cells and then added either GM-CSF or PMA to differentiate the cells before adding D-luciferin, which is a substrate. GM-CSF activates STAT5, and PMA results in a more M1 leaning macrophage. As you can see, that the GM-CSF differentiated macrophages, which would have had an increase in STAT5 activation, are more luminescent over the PMA differentiated ones. To test the M1 reporter line, I used PMA to differentiate these monocytes overnight to macrophages, and then changed the media and added D-luciferin. At time 0, I added TNF-alpha, which is a cytokine known to induce an M1 phenotype. As you can see by the curves, the stimulated cells had an increase in luminescence as opposed to the unstimulated phenotype, which this is caused by the stimulated cells having an increase in NF-kappa B activation. I also tested the M1 reporter line using imaging. I plated and differentiated the cells, and then added the substrate, took an initial image to show what the cells look like before removing the well and spiking in TNF-alpha. The luminescence immediately following the spike was higher than the unstimulated brightness, though it quickly decreased. We've discussed extrinsic factors like cytokines that can affect TAM polarization. However, the previous polarization of a macrophage, which is an intrinsic factor, can also affect this. So I used LPS, or tumor conditioned media, to stimulate, to cause a initial either M1 or M2 polarization before changing the media and adding LPS as at time 0 as a stimulation agent. As you can see, the cells that were preconditioned towards a TAM phenotype had a similar response to LPS as the unstimulated ones, suggesting that it's possible for tumor-associated macrophages to be repolarized towards an M1 phenotype. However, macrophages that were already exposed to LPS, which would stimulate cells that were already M1 polarized, did not increase their NF-kappa B activation as much as the unstimulated or TAMs did. So this is potentially similar to macrophages that have already been under inflammation. So this makes it readily apparent how necessary it is to understand factors that affect polarization, as well as test therapeutics on macrophages polarized similarly to as they will be in patients. So I've shown how bioluminescence can be used to measure macrophage polarization temporally, and intend on focusing on ways to optimize our imaging by finding a technique to introduce stimuli to the well being imaged, as well as utilizing bioprinting to make cytokine gradients. Eventually, I want to use this platform to test nanotherapeutics that attempt to repolarize TAMs into a more pro-inflammatory phenotype. Thank you.